I want to welcome you warmly, and today everything is about engineering the future, and I think nobody wants a future without a good drink. And therefore, we want to talk about climate change and carbon dioxide, but also about ethanol today. So, as this is going to be an alcoholic affair, I would recommend you to sit down and relax with a good glass of wine or beer, any poison of your favor, and I will give you some context. So there are three main questions we're dealing today with, and I'm also trying to answer in my PhD. So number one is, what could be done with all the carbon dioxide emitted into our atmosphere every day? Can't we do something useful with this, like ethanol? And number two is, what could be done with the surplus electricity which is generated temporarily because of the use of renewable energies? And number three, and I think it's the most interesting and most important question today is, isn't there a cooler variant to make boost than just the traditional way? And I think this is worth a shot. So the answer to all of these questions is electrochemical carbon dioxide reduction reaction with the help of gas diffusion electrodes to produce multi-carbon products. Yeah, this might sound insanely complicated, but it's not, I promise to you. So here we can see a cross-section of such a gas diffusion electrode, and you can imagine it just like, just as a distillery. And this distillery is the place where our magic happens, where we generate our ethanol and it's divided into different parts. Part number one is the gas diffusion layer. You can see it here, and it's just woven carbon fibers, and onto this woven carbon fiber web, there's a microporous layer, which is just a really thin layer made of PTFE and of carbon black. And then there's our catalyst layer. This is part number two. And our catalyst layer is really important because the catalyst is for the carbon dioxide, like the coffee is for me in the morning, because in the morning, I'm so tired, I'm so lazy, I don't want to do something, anything. I want to do nothing. And then there's coffee, and coffee says, Theresa, you can do it. You can do whatever you want. Just go outside. And carbon dioxide is also really lazy. It's a really stable molecule, and it also doesn't want to react, and it doesn't want to turn into ethanol. But then there's our catalyst, and our catalyst says, carbon dioxide, you can do it. You can turn into ethanol, and I think that's a really good message. So yeah, what happens in this gas diffusion electrode? So the gas diffusion electrode is installed into a normal electrochemical cell, just like a battery. So, and there you have the anode chamber and the membrane, the cathode chamber, and then our gas diffusion electrode. And then there's a third chamber. This is special. It's on the backside of the gas diffusion electrode, and it's our gas compartment. And there our carbon dioxide flows through, and it flows through this chamber and diffuses through our gas diffusion layer and our microporous layer to the catalyst layer. And there, where catalyst, electrolyte, and our carbon dioxide meet each other, there our alcohol is generated with the help of some electrons. And the produced ethanol you can find in the end in our electrolyte solution. And maybe you now think about drinking it just like a cocktail. No, don't do that, because I'm using 1 molar potassium hydroxide solution as electrolyte, so not the best idea. Please separate it before, really. So, but now we talked about our cell and about the gas diffusion electrode itself, and the question is what catalyst to use. What catalyst is working? And when we have a look at the periodic table, there are so many elements. There are so many metals, and yeah, you could just try some of them. The problem is, for example, silver and zinc, they only produce carbon monoxide, good for syngas, but no ethanol. And then we also could use tin, only or mainly formic acid. Okay, not what we want. Nickel and iron, they decompose our electrolyte solution. They don't even need the carbon dioxide, so we just get hydrogen. Also not the best idea, not for ethanol. But then there's one element, one metal, and it's a distillery master among the metals. And we know it because we often drink our Moscow Mule out of cups made of it. Could be a hint, I think. So it's copper. Copper is our distillery master, and copper is able to do the carbon-carbon coupling just to get multi-carbon products like ethanol. And it does this with the help of intermediates, which were generated before. Carbon monoxide intermediates. Carbon monoxide, yeah, zinc makes carbon monoxide, and therefore I also add some small amounts of zinc inside my catalyst layer or inside my catalyst itself, just to enrich the surface of this catalyst with carbon monoxide, which is made by the zinc, and then the copper can generate more ethanol because there's more carbon monoxide, which can be coupled by the copper. Okay, so now we got it. Here we go. Stop thinking, start drinking. But it's not that easy because of selectivity, of course. The selectivity is not the best the most time. There's a range of products which can be made. And when you work with this catalyst and electrodes, you realize everything has a huge impact. So at the moment, I'm relying the layer thickness of the catalyst layer, and I'm just trying to use different binders which sticks or holds the catalyst together. And I'm also using different contents of binders, and everything has a huge impact, and the alcohol level is rising, and that's great. And that's the reason why I will stay tuned, because maybe the electrochemical carbon dioxide reduction reaction is not the overall technique to fight climate change, but yeah, it can contribute to reduce the carbon dioxide into our atmosphere, and it's a step to more ethanol for all of us. And I mean, what could be wrong with that? So now I want to thank you, and raise your glass and have a wonderful day.